Hi folks. Today I have a question for you about how to calculate enthalpy change from bond energies. Right. For calculating enthalpy change from bond energies, we have to be provided or we have to use the bond energy values, which tells us the amount of energy required to break the bond between those two atoms that are connected together in a compound. So we are going to go for an example. We have an equation C3H8 C3H8 plus O2, and this is a combustion reaction, forms the CO2 and H2O, right? So this is a standard combustion reaction for C3H8, which is propane. Now, uh, before we calculate the change in enthalpy delta H for this reaction using bond energies, I just want to indicate that calculating delta H from bond energies is not a very effective or accurate method of calculating the enthalpy change of a reaction. The other methods, using calorimetry or using the Hess's law, are much more accurate. But in this case, we are going to try to attempt to calculate the bond energies or calculate the enthalpy change using bond energy. So in this compound, in this equation, we have C3H8, which is propane, plus O2 forms CO2 and H2O. Our equation is not balanced. So first, we'll take a few moments and balance our equation. We have 3 carbons on the left, so we will put a 3. And we have 8 hydrogens on the left, so we will put a 4. And now we have 6 plus 4 oxygens on the right hand side, now which is 10, so we will put a 5. And so this becomes a 1. So these are our stoichiometric coefficients for our balanced chemical equation for the combustion of propane. Now, we are going to try to solve for the enthalpy change using this bond energies. So to do that, we have to actually go into the molecule and identify the different bonds that are involved in this reaction. So in this compound, like for example C3H8, we know that there are 2 carbon-carbon bonds, and we have 8 carbon hydrogen bonds, right? And again, I can draw the diagram below so that I can show you how that is the case. When we're drawing propane, 1, 2, 3, and hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. We have these hydrogens here. We can identify that we have only 2 carbon-carbon bonds, right here, and the second one here. It's hard to see. I can highlight that. We have this one here and this one here. Those are the only 2 carbon-carbon bonds. For the carbon hydrogen, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 carbon hydrogen bonds, right? And that is how I got my information above. I have 2 carbon-carbon bonds and 8 carbon hydrogen bonds. And I'm just going to multiply it by 1 as a coefficient because I only want one of these molecules. The second one I have 5 O2s. So oxygen. What kind of bond do oxygens have? Oxygen has a oxygen double bond. Okay, so there's only one double bond between 2 oxygens. So we will have that in our diagram. We will have to find the energy for that. And again, if you would like me to draw, it will be O here, and then another O here, and that is what an O2 looks like. Okay, so we have that, and we have only one double bond in the middle, which is this guy here. And so that's what we have indicated above. So a single bond times 2 is not the same as the amount of energy for a double bond. So you cannot mathematically just take a single bond and times it by 2 or times it by 3 for a triple bond. They have to provide us with a fixed amount of energy for a double bond, and they have provided that. And for triple bond, they will provide that. And if it's a single bond, they will provide that bond energy, or the amount of energy required to break the bond. Okay, we have that, and now next we have CO2. And have 3 of those. So what kind of bonds does carbon dioxide have? Well, carbon, oxygen, and we have that. So we have 2 carbon oxygen bonds, right? Two double bonds between carbon and oxygen per CO2 molecule. And I can label that here, one there. So we have that. And we have three of these molecules. So I put a 3 outside the brackets. Plus our water. Our water is O and H and H. And then in this case, we have 4 of these waters. And each water has, again, labeling 1, 2. We have 2 OH bonds that we have to break to make those all, we have to determine the amount of energy required to break the bond. So we have 4 of those. So once we have identified this information, now we can go back to the chart and determine the bond energies. So the bond energies for C3H8, and I'm going to use the brackets here because it is nice and organized this way. We have 2 carbon-carbon bonds, so 2 times 300. Kilojoules of energy. That's the amount of energy required to break the bond. And 8 times carbon hydrogen, which is 393. Okay, plus 5 times O2. O2, we have to look at O and O double bond, which is 433. Okay, and now we have 3 times 2 times carbon double bond to the oxygen is 736 here in the chart, 736. Just to make a note here, in some charts they will give you a different value for carbon double bond to the oxygen in carbon dioxide. They usually give you a different value of 799 instead of 736. But in this case, since they have not given us that value, we will continue to use the 736 value for our calculation. Okay, plus we have 4 times 2 times the oxygen single bond to the hydrogen, and for that the amount of energy is 464. 464, and again you can write all the kilojoules here, kilojoules. Okay, now we have all the energies. We can calculate the sums on the left, sums on the right. Okay, and that's just a matter of just taking the calculator and plugging all the values in to find the numbers. 2 times 300 plus 8 times 393 plus 5 times 433. That gives me a 5909 kilojoules. And on the right hand side, it gives me, again, I just have to put all the numbers in the calculator. 3 times 2 times 7, 36, plus 4 times 2 times 464. That gives me 8128. Okay. Now, what we have to do is we have to figure out the bonds broken and the bonds formed, right? So on the left hand side, we have to break all these bonds. So this is to figure out delta H from bond energies. We have to figure out the sum of all the bonds broken minus sum of all the energies of bonds formed, which is equal to 5909 kilojoules minus this 8128 kilojoules, and that will give us the bond energy for this reaction as 5909 minus 8128 is negative 2219 kilojoules of energy. Okay, so that is the delta H or the enthalpy change for this reaction based on bond energies. I hope this lesson was useful. If you have a question or if you would like me to do another question, please post it in the comments below.